Half-life. Half-life is the time at which half of the original nuclei remain, and the second half is converted to a stable element or to stable nuclei. So, in general, n at a time t equals to t half, we must have n0, the initial of the unstable nuclei, divided by 2. Okay? So we can substitute the value of t by t half. We get n0 exponential minus lambda t half equals to n0 divided by 2. Here, I want to calculate the value of t half in terms of lambda and in terms of tau. Okay? In order to calculate t half, we use the decay law, nt, and we substitute the value of t by t half. Okay, here we can eliminate NO with NO, exponential minus lambda t half equals to half. To calculate t half, we can multiply by len and here by len. You know, len exponential x equals to x. So we get here minus lambda t half equals to len half. Len half equals to minus len 2. Okay, we can simplify this one. We get finally t half equals to len 2 divided by lambda. And you know, 1 divided by lambda equals to tau. So we can write tau times len 2, we get 0.69 tau. So here, the most important point is the value of t half in function of lambda. It's inversely proportional. And also the value of t half in function of tau. Okay, it's a direct, it's a linear, or it's a proportional to tau. Here I plot the value of unstable nuclei in terms of the time. You know, at one period, one half-life, the number of the unstable nuclei equals to n0 divided by 2. At 2 t half, the second t half, the number of the unstable nuclei equals to n0 divided by 4, and so on. For example, here if we have initially n0 equals to 100 unstable nuclei, at t half we get 50. Okay, for example, here we have t half. At this point we get 50 unstable nuclei. The second t half, or 2 t half, we get 25. At 3 t half we get 12.5, for example, and so on. In general, after 7 t half, all the unstable nuclei decay to stable nuclei. At 7 period, we get a 0 unstable nuclei and n0 stable nuclei. Okay, so all the unstable nuclei is converted, or the n0 is converted to n0 stable. N0 unstable decay to n0 stable. Anyway, n is the number of half-lives. How many half-lives are used? We can write the relation between n equals to n0 divided by 2 power n. So for one half-life, n equals to n0 divided by 2 power 1 equal to, so we have n0 divided by 2. At n equals to 2, or uh, at time t equals to 2t half, okay, we get here n equals to n0 divided by 2 power 2 equals to 4, and so on. Okay, we can go to n equals to 7. At this point, we get 0 unstable nuclei. Okay, this is the first point. The second point, what is the probability of decay? Is delta n divided by n. So the probability of decay is delta n divided by n, and lambda, you know, lambda equals to minus delta n divided by n divided by t. We can say is the probability of decay per unit time. We talked about lambda before. We can say decay rate or the probability of decay per unit time. Probability of decay delta n divided by n, and lambda is equal to this value per unit time. Anyway, now it's very important. We have a relation between the half-life and lambda with half-life and tau, and the relation between these parameters. In general, if we take this one, if lambda is large, so t period is small, half-life is small. What I mean, if we have a large probability of decay per unit time, so we lose, or we have a decay process quickly. We can lose quickly the total number of unstable nuclei to a stable nuclei. We can say for a large number of lambda, we get a small value of t half. We get the process of decay quickly. Okay. Also, in this case, if we have a large number of lambda, we have a large number of probability of decay, and in this case, n decreases fast. It means we lose fast the number of unstable nuclei to a stable nuclei, or to stable nuclei. Here we can calculate the activity in terms of half-life. You know, activity equals to lambda n t equals to lambda n0 exponential minus lambda t equals to, you know, lambda n0 equals to a0 is the activity of decay at initial time. Okay, so we get here at equals to a0 exponential minus lambda t. What is the value of a after a 1 half-life at t equals to t half? Okay, we can substitute the value of t here. We solve it. You know, here we put t equals to t half, and you know lambda equals to ln2 divided by t half. Okay, you know t half equals to ln2 divided by lambda, so lambda equals to ln2 divided by t half, and we get finally a0 divided by 2. So the value of activity of disintegration per unit time decreases to half of its original value after a time t equals to t half. Okay, if we get a relation between a and t, after a time t equals to 1 t half, we get here a value of a equals to a0 divided by 2. If we have 2 t half, so we get here a value of a0 divided by 4, and so on. Finally, we arrive at t equals to 7 t half, we get 0 activity, because we will not, all the unstable nuclei are converted to a stable nuclei. Okay,